Welcome to another episode of Code for Thought. If you're looking for the city of Kajaani in Finland on the map, you'll find it right at the heart of the country, not far from the Baltic seaport of Oulu. Kajaani, as it happens, is the location of a supercomputing center called LUMI, which according to the website is the fastest supercomputer in Europe. Funding comes from the Euro High Performance Computing Joint Undertaking, or in short, EuroHPC-JU, also the Horizon 2020 Research and Innovation Programme, and from the participating states, one of which is Belgium. And this brings me to Kurt Lust from the University of Antwerp in Belgium. Kurt is part of the user support team for LUMI, and in the following interview, he's going to spill the beans about what it takes to run and manage a computing beast such as LUMI. I met with Kurt earlier in 2024, just after he paid the supercomputer a visit, alas, without being able to see much of the machine, as he will explain in our conversation. So over to Kurt.
Well, my background is in computer science and mathematical engineering, basically numerical mathematics and scientific programming. I started my career in the supercomputer world, but quickly moved to more numerical algorithm development without specifically eyeing supercomputers from the start, though they were suitable for supercomputers. But then in 2008, I moved back to completely working into supercomputing. First at KU Leuven in the framework of the Flemish Supercomputer Center, then from 2015 on at the University of Antwerp, where I also got more and more in touch with international projects. And so at the end of 2020, I also ended up as a half-time person in the LUMI user supercomputer support team.
You've got us right into the subject we want to talk about, which is, of course, your half-time, or the half-time you spent at LUMI. I think it stands for Large Unified Modern Infrastructure. So I had to look it up. And could you explain what you do there? You mentioned support.
Yes, so within LUMI, I am one of the people of the central support team. The LUMI only has a fairly small central user support team, about 10 full-time equivalents, but with people from all consortium countries that contribute to paying for the LUMI project. The LUMI project is a European project run by the EuroHPC JU, and it's one of those projects where the GU funds 50% of the cost and the other 50% has to come from states. And in this case, it's 10, by now 11, the Netherlands joined in January of this year, countries that pay the other half of the expenses. But to have some return to those countries also at the level of knowledge and not just at the level of cycles, people from the LUMI user support team come from the various countries. At the moment, there's 19 people.
You're obviously in the contingent for Belgium, I guess.
Yes, for the Dutch-speaking part.
Oh, for the Dutch-speaking part. The supercomputer is based in Finland, isn't it?
Yes, it is located in central Finland in a city called Kajaani, close to some big lakes with lots of water, and especially one of the few places in Finland where you have enough altitude differences that you can have water power for electricity.
And you've been recently there.
I have, yes. Unfortunately, I didn't get to see the computer itself because it just happened that week they were replacing the cooling liquids in the nodes or in the computers, and since that can give fumes that are not too healthy, we were not allowed in the room itself. I've seen the outside container, I've seen how it's constructed, and I've seen the technical installations through the window, but I haven't seen LUMI yet itself.
Since when is it in operation, or is it in operation at all at the moment?
LUMI is in operation, yes. The GPU partition is now a year and a half in full operation. Well, it's those big machines, they tend to come up gradually. So at first, only the CPU partition was installed, basically because the GPUs were not yet available in sufficient numbers, partly due to delays due to COVID and manufacturers of essential parts shutting down. And then later on, the GPU partition got installed, but then, of course, you have the run-up with all the technical issues that need to be solved.
Like what?
There is a pilot phase, then it becomes officially in production, but actually when it came into production, the machine was not yet accepted. And so it saw yet another extension to pay for the late delivery and the late acceptance. and the slightly lower than expected performance of the GPU. So we got another bunch of CPU nodes and another bunch of GPU nodes for all that.
All right, okay. I think we're probably going to come into the whole GPU, CPU discussion a little bit later. But what I would also like to touch on is, you mentioned hydropower and all of that. The reason I'm interested in it is because there's a growing concern, or a growing interest, I should say, of people in the environmental impact of computing. And I think from that point of view, the data center in Finland, in Kajaani, may actually be quite interesting, because isn't that supposed to be zero carbon or carbon neutral? Or can you tell us something about that?
You can discuss about carbon neutral forever, because which factors do you count and which factors do you not count? But I think I can say that LUMI is one of the greenest machines in the world, definitely. So it even starts with the construction of the machine. They did not build a completely new data center. They basically started from a concrete hall from an old paper factory that was no longer used. So that already means that they saved a lot of concrete, and even producing concrete produces a lot of CO2 because of the production process and the heat needed in it. But then LUMI itself is, like any modern system, water-cooled, can handle fairly high water temperatures, which means that if you are in a relatively cold place like Kajaani, they were proud that their hottest temperature last year in summer was 26.3 degrees, which was reached for one day. So that means if you're happy with water of 35 or 40 degrees entering the machine, you just have free cooling year round.
Yes.
So that also saves a lot of energy. Those compressors that you need to extract the heat otherwise really consume a lot of energy. Then the other, of course, you are using green energy in Finland. Officially, we're buying water energy, but of course, you never know where your electrons come from.
Not really.
Of course, they should not sell electricity they cannot produce. But so that's yet another aspect. But then yet another aspect is that they even try to reuse the heat from the machine. Kajaani is a city which is big enough that it needs a fair amount of heat, especially in the winter, to heat the place. And like more cities in Finland, it still has a central heating network. And so 200 meters from the data center, there is a plant that was used to produce heat. And so they sent the hot water from LUMI to the plant, where it's fed to a heat pump to bring it up to the temperatures that are needed for city heating. So part of the waste heat, especially in winter and early spring, late fall, is used to heat the city of Kajaani. It's hard to factor in, of course, how much that makes. And on one hand, if you look at the traditional parameters that define efficiency of a data center, it makes the data center worse. Because to make that reuse possible, they have to pump around a bit more water than would really be good, and over longer distances. That increases the energy use at the data center. But then if you look at how much you gain from the heat that's recovered, and if you factor that in, then LUMI indeed is a very green machine that consumes less power than you would expect if you subtract the power that goes into the heating of the houses.
I think it's probably benefiting from geography, because obviously
is a good place to put computers. Yes, there's some kinds of green energy are easier to produce there, but well, anyway, you don't want to run a supercomputer on solar energy because you don't have solar energy at night. So you need things like water energy and so on. A cool place is, of course, always better for the cooling, and it makes it easier to reuse heat. Though if I look at the plans for the whole site in Kajaani, they hope to have a successor of LUMI, which will consume 3 or 4 times more power, is the expectation. But they also hope in a nearby site to attract another big data center developer for a data center of a few hundred megawatts. Obviously, that's too much heat to send it in the city network, but there again, Finland tries to be innovative. They're looking at how can we use it to heat greenhouses, or can we use it for fish farming in tanks? Then, of course, they will not heat the lakes. That would be unacceptable. So they are really looking at ways to use the heat from a data center in an optimal way to reduce its effective carbon imprint.
You mentioned that the power of computers is going up, or is expected to go up, and with it, of course, the energy needed. And there's been a report, I think it was in The Economist or in one magazine that I saw recently, that the big players in the US, like Alphabet and Meta and all the other ones, almost need their own power plants in future to run data centers. Why is that?
We want more and more compute. And we want that compute to be portable, which means that you cannot process everything on your device. And new applications like AI and so on, the dreams people have there, are really crazy. So on one hand, we want more and more compute. On the other hand, we may be used from what we've seen between 1980 and 2010 was a very quick evolution where you got more and more compute power for the same amount of money and for the same amount of power. That evolution has ended long ago. People always talk about Moore's law, which they have changed a few times because it didn't match reality anymore. But there is a much more important law in computing and semiconductor design, and it's called Dennard's law. And that kind of scaling that Dennard predicted is no longer valid either. So if you now further miniaturize, with every new process, initially it was like half the power, 30% or 40% more clock frequency, half the size of a cell. This is no longer true. The way the miniaturization goes now in every process step, you've got not even a doubling of the number of transistors anymore per square centimeter or per square inch. The power per transistor hardly goes down, the performance per transistor, so the switching speed hardly goes up, the clock speeds that you can reach hardly go up, but the cost of the transistor also hardly goes down anymore, or doesn't go down at all anymore. So since 28 nanometer processes or so on, the cost per transistor or per logic gate has mostly remained fairly constant. And this means right now that if you want more compute power, you cannot get that much more work done per transistor. So it means you need more transistors, you need more power, and you need more money to keep everybody satisfied until the system will crash eventually because there is no economic advantage to it anymore.
So let's switch slightly to the kind of applications that are running on LUMI at the moment.
Basically, almost everything you can imagine. LUMI is a quite versatile infrastructure. People, of course, would like it to be even more versatile. There are always people with very special needs, but the CPU section is overused, is over-demanded at the moment with long waiting times as a result because they've handled it too high oversubscription in allocating projects. And you see everything there, all classical domains of simulation, earth sciences, whatever you can imagine, it's there. The GPU nodes are also quite well used recently, and that's the mix that you could expect. It's not all AI, there's lots of simulation going on there also. And it goes from very small projects that typically come in via the participating countries to huge projects where EuroHPC has had a flagship project that consumed 10% or more of all resources of LUMI. So it is a complete mix.
Is the kind of applications that are running at LUMI then divided by, well, this one runs on CPUs and this one runs on GPUs, roughly speaking?
To some extent, though, you have codes that have both CPU and GPU versions, and for some problems, the GPU version works well. For other problems, the GPU is just too powerful, or it uses functionality in the code that doesn't work as well. But many projects are either CPU or GPU, but not that many projects that use a mix of both. That's true.
Maybe we can talk a little bit about the allocation, because you mentioned that different countries and obviously the research institutions within them would like to have their programs or their applications run on a supercomputer like LUMI. How does this work? How does this allocation work? Is every country getting, say, a particular time slot or a piece of the cake, or how is this divided? Do people have to apply for it?
It is not the supercomputer itself which is cut in slices, like this country gets that many nodes, nor it is a kind of time slicing, like today Belgium gets the supercomputer, tomorrow the Netherlands get it, and the 5 days after, because they have paid so much more, Finland gets it. That's not how it works. It's like a completely shared resource which can produce a certain amount of compute time each year. And that compute time is divided among the participating countries and EuroHPC proportional to their investment in the machine. And so each consortium country is free to organize its own access program, of course, within the limits of the machine. And if for some node type we only have a few, they're not supposed to assign one particular project that might monopolize that resource, like we have a few data analytics nodes. And they have been abused in the past by a single user who tried to run everything on those nodes. So that's, of course, not what should happen. In the case of EuroHPC, for instance, they have several access programs, typically like a benchmarking access or a code development access, benchmarking typically for 4 months or so to see if your software runs and if it runs well on the computer. Development, if you're really developing new software packages, then typically you don't need to run that much, but you need a computer for a long enough time to be able to do anything useful. And then depending on the allocation that a country has, they then typically have various channels of access depending on a lightweight procedure if you need smaller access, a heavyweight procedure if you need very long access, really need a lot of resources. Like EuroHPC has its regular calls and then has extreme calls, and the extreme compute calls are really projects that may be worth $1 million or more in compute time.
All right, okay.
And then apart from that, if it's not for open research, companies can buy compute time. The EuroHPC target is like 20% industry use, but that of course includes both open use and time that is really sold to companies. But even then, it remains a research infrastructure, and the quality of service is that of a research infrastructure and not that of a production infrastructure. So you don't want to run your Met Office load on there, or you would have weeks without weather forecast. Or an industrial company doesn't want to run their really time-critical things on there. That's what the commercial providers or dedicated infrastructure is for.
Exactly, yeah. But they can, for instance, if they have a research project, which companies, of course, do as well, then they can use that, sort of the kind of 20% mark, which you
and
just
certainly
mentioned.
Finland has been quite successful in that, has attracted quite a lot of companies also already. Companies that need simulation and companies that do AI. Like some companies want to use LUMI to train a model, but you need to do that only once, and everything after that is inference, which they then do on their own infrastructure. Or they even simplify the model then to be able for their clients to run it on their laptops, on their PCs, on their smartphones.
Let's talk about the nodes then. How many nodes do you have?
At the moment, we have just over 2,000 regular CPU nodes and close to 3,000 GPU nodes. So those GPU nodes each have, depending on how you look at it, 4 or 8 GPUs, because the GPU is a 2-die solution. And really, for all practical purposes, the 2 dies behave pretty much like independent GPUs. You kind of program it like it's an 8 GPU node.
What can you tell us about the architecture of these machines?
So in the case of LUMI, the GPU is not the usual NVIDIA GPU, but it is an AMD GPU. And it is even one which is built specifically for, when they started building it, it was still Cray. It was before the merger with HPE. So the GPU exists in 3 versions, and only one of those versions is specifically for Cray. What is specific about the version for Cray is that they also built a matching CPU, which is basically a Zen 3 CPU, but with a slightly modified I/O die that can use the same fabric that is used to connect GPUs together, or that AMD also used to connect their CPUs in dual CPU nodes, but uses the same fabric to also connect to the GPUs. And this is a technology that was first explored in the pre-exascale systems of the US, which happened to be built by NVIDIA with IBM. And with a modified IBM processor that had NVLink between the CPU and GPU. But the result of that is that you have that the caches can talk better to each other, so you have some level of cache coherency, and you have much more bandwidth than in a typical PCI Express connection between CPU and GPUs. So
I would like
if you look at the total bandwidth to the GPUs from the CPU, it's basically the same as the memory bandwidth of the CPU.
So what are the challenges then when you put something together for a supercomputer center?
Scale is an enormous challenge. The larger you build the machine, the more you need to pay attention to all kinds of fine details. It already starts with you want the nodes as close as possible to each other, which means that you have an immense heat production in a very small area. So
Indeed.
the slide I typically show during a training has 4 compute racks and a cooling rack. And those 4 together take about 12 square meters. And that produces on the order of 1.2 megawatts at full load. So that's really an enormous power density. Why do you want that power density? Well, one factor is the closer nodes are together, the faster they can talk to each other. We see light as something which is very fast, and indeed, in the time that you do a double step, light has traveled a distance which is like equivalent to 8 times the circumference of the Earth. But if you look at light at the scale of a computer, your smartphone, a low-end smartphone, has a 2 gigahertz processor. Distance that light travels in one clock cycle is 15 centimeters. It's not even from one end to the other end of the long side of your smartphone. So you can see with computers with gigahertz processors that light is slow and that data transfer, that distance is indeed an issue. Moreover, the shorter the distances, the cheaper your cables. You just have to look at the price of USB cables and how much, or Thunderbolt cables, and how much more expensive they become if you want them a little longer, to realize what the problems are at the scale of a supercomputer. These are yet more expensive cables. So everything is done to reduce those costs and to optimize communication. But then you also need a very fast network to connect all those elements together so that really everybody can communicate properly with everybody. In the case of LUMI, this translates in on the order of 1,000 network switches, which is huge compared to your small university cluster, which probably has 20 switches. So quite often a switch breaks, and whenever a switch breaks, this can cause a disturbance somewhere in the system. The system should be able to overcome that automatically, and it does, but still it's like a momentarily performance loss for some programs. Or you need to be very careful if you want to run a program on 1,000 nodes that the OS doesn't cause any jitter that can slow down an application in a random way, because at one point it may slow down on one node, on the other point it may slow down on another node, but all those nodes run more or less synchronously in a big parallel application and at the speed of the slowest. So it means that at any point in time, if there is one node slow, your whole application slows down. These are all things that need to be taken into account, and it's actually sometimes hard to explain to people who come from a background in a small university cluster why LUMI cannot offer them certain features that they are used to. Basically because of scale, because they don't scale to the machine level of LUMI.
Yeah, no, I'd like to understand that a little bit more, and maybe the listeners do, because it's the kind of resilience aspect. Because if you have thousands of nodes, CPUs and GPUs, the chances that one of them actually goes down or slows down is not unrealistic, shall we say, during the duration of a program. So how does it recover then?
Mostly automatic. The thing is, usually most applications use only a part of the cluster. You rarely have something that runs on the whole cluster. Since the nodes are fairly independent, if a single node crashes, only the program that's running on that node is affected. And those nodes are automatically detected by the scheduler and the resource manager. They see, hey, this node is not responding anymore. I should not try to launch any new job on them, and I'll warn the sysadmins that they have a look at it. So at that level, it's all fine. But of course, if you have a job that uses 1,000 nodes, and you have on average 1 out of 1,000 nodes crashing a day, then the chance that that 1,000 node job can run for several days without being interrupted is close to zero. So you need a kind of resilience at the level of the user software also. And then another funny problem that we experience, but not only we, I recently talked to my colleagues of Leonardo, who had a completely different vendor of storage and a completely different network vendor, but use the same storage technology, the same parallel file system. And we do notice that sometimes it freezes for 2 minutes, and that seems to coincide with the crash of a network switch.
All right. Okay.
Even though the network recovers automatically and Lustre recovers automatically, it's like 2 minutes that on some of the nodes, the file system completely freezes. So mostly recovery is fairly automatic, and most crashes stay local. Don't take down the whole machine, but the larger the fraction of the machine that your application uses, the higher the chance is, of course, that you're affected by any single problem. 15 years ago, they forecasted that the exascale machine would not be useful unless you went to new programming techniques. Nobody believed, but we see on LUMI that there is indeed a reliability problem at the scale of such applications.
That reliability problem, so how likely is it in the course of operations, if one can say it in a single number? Probably not, but how likely is it that something goes wrong, say, within a day?
Depends on the size of your job, of course. If you're running on a single node, then it's quite unlikely. If you're running on 1000 nodes, I would have to do the computation again, but I think it was like only 30% or 37% chance or so that your application survives that day.
Wow.
They did figure out that part of the problems come from overheating of GPUs and problems in the cooling system. And that's why I wasn't able to see LUMI when we visited it 4 weeks ago. They were trying to fix those problems with the cooling system. It's not uncommon. I heard on Frontier that they are quite used to have one node failure every 12 hours, but they have 3 times more nodes than LUMI has.
So it's not only LUMI, it's also the other centers.
Yeah, it's typical for, any big machine.
Yeah.
If a server happens to fail once every 3 years, of course, we all know that it's a bathtub, that it's a lot of failures at the beginning and a lot of failures at the end, but even in between, some nodes fail. But then if you multiply that scale with a factor 20 to come to LUMI, of course, you have 20 times as many node failures.
Do you actually mark then some time during the year where you say, okay, LUMI is going to be down, or at least part of LUMI is going to go down for some maintenance, like, for instance, machine needs replacing or some hardware needs fixing?
Yeah, well, centers can have different policies there, and some centers have regular small downtimes. We don't have those on LUMI, but we do have big downtimes every now and then for a big software refresh. Basically, when you need to touch the management environment of the system, or when you need to touch the basic software of the storage system, you need to take the machine down. So we had a week of downtime during the Easter holidays to update all file system software. We will have a downtime by the end of the summer, early fall, which may probably coincide with the moment that this is being broadcasted. And that will be a long one because they really need to update all software on the system.
And it's the software part that we haven't really talked about very much so far. You mentioned the software. What kind of software? Is it the operating system that you're talking about, the update, or particular applications?
Part of it is the applications user-level applications are separate. That only happens afterwards. But the whole software infrastructure of a cluster is quite integrated. You have your whole management environment with the servers to start jobs and so on, and lots of services that keep track of the machine, also keep track of which nodes are down, which nodes are close to breaking down. To start the machine, you don't just start it by triggering a switch. Well, that's what you want, of course, and that's what happens, but that only works because there is a lot of software there that will then start the nodes one by one, make sure that they have the correct system image, and so on. So it's all much more complicated than on your workstation. People think that supercomputers run Linux. They do, but Linux is not a supercomputer operating system. It lacks a lot of features that you need to run a whole supercomputer. It lacks management features, so they run on the management nodes. It lacks scheduling, resource managing at the level of a supercomputer. Linux basically manages only a single system image rather than 5,000 system images collaborating. Then there is lots of software that is not part of basic Linux, but that is essential to write parallel programs like an MPI library, like OpenMP runtimes. So all those things have to match with one another and are replaced together.
And how do you manage that, if I may ask? So in addition to Linux, you basically have to make sure that Linux operates on all the nodes.
We turn off some features of Linux because they produce too much OS noise or OS jitter, as it is called, which would slow down large parallel applications. That's another thing that users don't always realize, that when they come on LUMI, it's Linux plus a lot of other things and minus some things that they're accustomed to from their workstation.
Where is all this management software then coming from that brings all this together? Is this written by people like you, or is there some kind of libraries that are available that people can then use?
No, I'm on the user side, and in our case, it's basically the cluster, the supercomputer manufacturer who also develops that management software. There are neutral companies that try to build management software, and there is a lot of open source work going on. So actually some of the components come from open source or are semi-open source, like the scheduler is developed by SketchMD, which of course has to make money from offering support, but at the same time, most of the code is open source. Some other components, like in our programming environment, there is a mix of fully open source components and then open source components with plugins that come from the cluster vendor. But there's always a company that has to merge everything together and write the missing bits and pieces. And in our case, that's Cray, but there have been independent companies that try to do such things.
The interesting question really is how much of that is open source. You alluded to the fact that some of it is open source, but not all of that.
It's built out of a lot of open source components, but the sauce that binds everything together is definitely not open source, at least not in the case of LUMI. What is happening though is that because Cray is used to get contracts from the big American science foundations or funders of supercomputer, and they are more and more into open source, so they are pressuring HPE, current owner of Cray, to put some of those components in open source, but then you're mostly talking about the more user-facing components. So those components that are important to have program portability, to move your program to another supercomputer, they are more and more being open sourced.
The final question that I have is, when you have software running, I mean the applications, how much in your experience are they actually making use of parallel computing abilities of the supercomputer?
No, and it's very hard to say because we respect the privacy of the users, and so don't go look into their jobs to see what they are doing. But on Lumia, from the experience that I have of seeing the projects that come in from my own country, most software is parallel at some level. But you have parallelism at multiple levels, of course. You have just being able to use multiple cores, and most modern software satisfies that. Then you have the distributed memory computing or the GPU computing. GPU computing is already trying to find even more parallelism in your application, and that's already a bit less. And then there is the other dimension, distributed memory parallel computing, being able to use more CPU nodes or more GPU nodes. But there's quite a lot of applications that can deal with them. Though we don't only have such users on LUMI, then we have some users on LUMI who could work on no other machine in Europe, except probably the other two pre-exascale machines, because their job is so nicely parallelized that it can make use of literally 1,000 GPU nodes we've had.
Is there a shortage of people in HPC? Do you see that in people with expertise, how to run and work on these supercomputers?
There definitely is a shortage, and fortunately more and more universities are also setting up programs to, like, masters in high performance computing and so on. EuroHPC itself has set up a collaboration between universities that organize a big master program with some mobility. People study the master for 2 years, but the 2 years are not in the same university, so that they get different ideas. What we see in then a university in Belgium who has set up such a program and moved it entirely towards large-scale data processing. With the AI hype, students are very motivated to go into that direction. It has actually become a pretty big area, so there I'm quite optimistic that in those fields, people may actually be able to find people in the future. You need two kinds of people. You need the people who are familiar with the basic technologies and can write very good programs and so on and help people with that. But then, of course, you also need the people who sit in between those people and the people with domain expertise in a specific science domain. And that can link those both things together, know enough about molecular dynamics to understand the problems of the molecular dynamics people and the models they want to use, and know enough of the computer to be able to write good software for that. And those people are even more difficult to get. Computational science should be multidisciplinary, but too many computational scientists really focus on the science and not enough on the computational aspect, while the computational aspect is more and more becoming the bottleneck. More and more of the future will be determined by better software. We need a change at multiple levels. It's the teaching programs that are not okay, but it's also the mentality and the way people are evaluated for the work they do. If you get no appreciation for writing a proper code, you will not do it. And then the third, I think, a mentality change that's also needed is that people think that everything is as easy as running an app on a smartphone, but that's not the case when you talk about scientific computing. You should see that computer as an instrument which is as complex as some complex measurement equipment or so on that the more experimental scientist uses.
I would like to thank you very much for your time today, Kurt. That was a fascinating talk, and all the best for the future at LUMI and for yourself.
Okay, thank you.
So if you're a researcher who runs an application on a supercomputer like LUMI and things don't go according to plan, spare a moment or two on the support team members who are working hard to keep the lights on. If you're interested in finding out more about LUMI and the EuroHPC Joint Undertaking Program, go to the show notes where you find the links. And as always at the end of the program, you can leave a review in your podcast app or contact me directly from the app, or LinkedIn, Mastodon, Slack, Matrix, or by email. If you'd like to support this podcast, go to my Patreon page, Code for Thought. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.